Welcome to part two of the video podcast series dealing with solution stoichiometry. How about advanced functional stoichiometric processes as a subtitle? We're going to get into some stuff. Welcome. In part one of the solution stoichiometry series, we dealt a lot with how to get to the mole when given a volume of solution and concentration of the solution. So the mole will always be a priority in stoichiometry. In mass stoichiometry, we've been given a reactant or product's mass and we convert to moles so that we can predict the amounts of other reactants and products. We cannot compare masses directly, but we can compare quantities of moles directly, and that's the whole function of a balanced equation and our stoichiometric calculations. In gas stoichiometry, we're given the volume of a gas and its pressure temperature conditions, and we convert it to moles to predict the amounts of other reactants and products. And so these are the priorities, is to get to the mole. As a reminder going into this, in solutions, if we're given a reactant or product's volume and concentrations, we can convert to moles and use that to predict the amounts of other reactants and products in the reaction. This is best considered in the context of a sample problem, so let's consider the following reaction. Here we're going to mix two solutions together, aqueous lead-2 nitrate and aqueous potassium chloride. And when we do that, we're going to form a precipitate, a solid, of lead-2 chloride because lead and chloride aren't compatible in aqueous solution. And then we will also have potassium nitrate that will remain aqueous. So our problem is what mass of the lead-2 chloride is produced when 125 milliliters of a 2 mole per liter lead-2 nitrate solution is reacted with excess potassium chloride solution. Our first step will be to set up a BCA table for the reaction and find the moles of lead-2 nitrate. So following through with step one, we have our BCA table set up for the reaction, and then we find our moles of lead-2 nitrate by taking our volume times the concentration in moles per liter of lead-2 nitrate. When we do that, you see the equation below that represents this. We get 0.250 moles of lead-2 nitrate. Now in the BCA table, we can just write that as 0.250 because it's understood that in a BCA table, the quantities expressed will always be moles. So we've done step one. Our next step will be to complete the BCA table for the reaction, and we're going to use mole ratios to find the quantities of the other reactants and products. Now, down below, what I'm showing is the 0.250 moles of lead-2 nitrate, and we're going to find out in our change line how many moles of KCl are going to be used. The mole ratio from the balanced equation is 2 moles of KCl for every 1 mole of lead-2 nitrate. So we multiply that mole ratio by the 0.250 moles of lead-2 nitrate that we found in the first step, and it gives us 0.500 moles of KCl. Now, the wonderful news in this particular reaction is that there are only two different coefficients. We have 1 mole of lead-2 nitrate for every 1 mole of lead-2 chloride, and we have 2 moles of KCl for every 2 moles of potassium nitrate, KNO3. If we know the amount of change for the lead-2 nitrate and the potassium chloride, because lead-2 chloride shares a coefficient with lead-2 nitrate, it will change by the same amount, only in the positive direction it's forming. And because KNO3 shares a coefficient with KCl, if we know by how much the KCl changes, that's the same amount of change, though in the opposite direction it's going positive in formation for the KNO3. So we can go ahead and complete our BCA table, and when we do that, we have at the end of the reaction 0 moles of lead-2 nitrate. It's the limiting reactant. We have excess KCl that was established early in the problem. We'll have 0.250 moles of lead-2 chloride that formed and 0.500 moles of potassium nitrate. Now that we have filled out the BCA table, our last step would be to convert the moles of lead-2 chloride, PbCl2, to grams of lead-2 chloride. So we take our 0.250 moles of lead-2 chloride, multiply it by the molar mass of PbCl2, which is 278.11 grams, over the 1 mole of lead-2 chloride. The PbCl2 in terms of moles cancels, and we're left with grams of lead-2 chloride, which is 69.5 grams of lead-2 chloride. Want to show you an alternative solution. We have worked a lot with BCA tables, and the BCA table is really a priority for us because in it we use our mole ratios, we find out everything about the reaction that's possible. Now, when we're dealing with limiting reactant problems, the BCA table is really a necessity for us. It's the easiest way to solve those problems. But this is not a limiting reactant problem, and there is an alternative solution. And so I want to show you the alternative solution, and you use the solution that you're most comfortable with. Either way is acceptable as long as everything is properly labeled. So for our alternative solution, we're just going to combine 3 steps. The first step was to convert moles of lead-2 nitrate, or convert 2 moles of lead-2 nitrate by multiplying the volume in liters by the concentration in moles per liter. Then we convert to moles of lead-2 chloride by multiplying by the mole ratio of lead-2 chloride to lead-2 nitrate. Once we do that, we then convert moles of lead-2 chloride to grams of lead-2 chloride. You'll see this expressed on the next slide. So here is the alternative solution, and you'll notice the asterisk saying don't use this if the problem involves a limiting reactant. There's reasons for that. I think that you understand. So what we have here is the first step. We take our 0.125 liters of lead-2 nitrate times the molarity, 2 moles of lead-2 nitrate per liter. Rather than putting an equal sign and saying how many moles there are, we just go to the next conversion, which is to multiply by the mole ratio. In this case, it's 1:1, which is very convenient for us. So we have 1 mole of lead-2 chloride over 1 mole of lead-2 nitrate. If we were to stop here, the unit in the upper right-hand corner of this expression is what we're left with, which would be moles of PbCl2. But we're interested in grams of PbCl2, so we're going to introduce one more conversion factor into the solution, 278.11 grams of lead-2 chloride over 1 mole of lead-2 chloride. When you look at this expression, the liters cancel, the moles of lead-2 nitrate cancel, the moles of lead-2 chloride cancel, and you're left with grams of lead-2 chloride, 69.5 grams of lead-2 chloride. If you can see this, you're welcome to use this. The BCA table, I think, organizes your information in a simpler way, and you're less likely to go wrong using it. But if you can see this alternative process, you're welcome to use it as long as everything is properly labeled. Let's look at another nuance to a solution stoichiometry problem. We're going to use the same reaction, but in this one we want to find the volume of a 3 mole per liter potassium chloride solution. We want to know how much of that we need in order to completely react 125 milliliters of the 2 mole per liter lead-2 nitrate solution. Step 1 is the same as in any other stoichiometry problem. We're going to get to the mole unit for the quantity that we know. The quantity that we know we have in terms of a volume and a concentration is the lead-2 nitrate. So we're going to set up the BCA table for the reaction and find the moles of lead-2 nitrate. So here is step 1. We've set up the BCA table for the reaction, and below the table you can find the conversion where we take our 0.125 liters and we multiply that times the 2 moles per liter of lead-2 nitrate, and we get our 0.250 moles of lead-2 nitrate. We put that in the before part of our BCA table, and now we're ready to move on. Once I have the moles of lead-2 nitrate, I can complete the BCA table for the reaction using the mole ratios. And so I'm going to take my 0.250 moles of lead-2 nitrate. I always go left to right, so I'm going to multiply it by the mole ratio of 2 moles of KCl over every 1 mole of lead-2 nitrate right from the balanced equation. And when I do that, I get 0.500 moles of KCl. What that tells me is that I need exactly 0.5 moles of KCl to completely react the lead-2 nitrate. So I fill out my change line, but I also know that I want the exact amount to react it. I don't want excess here. So I'm going to have 0 left, which means in my before line I can go ahead and put that I need 0.5 moles or have 0.5 moles of KCl in this reaction. The rest of the table is filled out as per the protocol we always follow when filling out BCA tables. And so here we are ready to go on and complete the problem. Our final step in this problem is to convert the moles of potassium chloride to liters of 3 mole per liter potassium chloride solution by multiplying by the molarity flipped upside down so that liters is on top. So in our before line we found that we needed 0.5 moles of KCl. So we're going to take our 0.5 moles of KCl times the molarity flipped upside down, 1 liter on top, over 3 moles of KCl. Our moles of KCl cancel, and we're left with 0.167 liters. So if I want to completely react the lead-2 nitrate, I would take 0.167 liters of a 3 mole per liter KCl, and that would exactly be the amount needed to completely react the volume of 2 molar lead-2 nitrate solution that we started with. Well, just as there was an alternative solution to using a BCA table for the first problem that we did, there's also one for this. It involves combining 3 steps. First step is to convert the moles of lead-2 nitrate, to convert to moles of lead-2 nitrate by multiplying the volume in liters by the concentration in moles per liter. Then we convert to moles of KCl by multiplying by the mole ratio of KCl over the lead-2 nitrate. And then finally, we convert the moles of KCl to liters of the 3 mole per liter KCl solution by multiplying by the molarity of the KCl solution flipped so that liters is on top. And you'll see that expressed in the next slide. So here is the alternative solution. Again, our first step to get to the mole, so we get to the moles of lead-2 nitrate, we multiply by the mole ratio, 2 moles of KCl to 1 mole of lead-2 nitrate, right out of the balanced equation, and then we multiply times the molar concentration of KCl flipped upside down so that volume is on top. As we do this, we get to our 0.167 liters of the KCl solution. Okay, so that is our goal, and we have 2 ways to get there. Use the way that you're most comfortable with. Well, this is the end of part 2 of the Solution Stoichiometry video podcast series here at Ontario High School. I want to leave you with another quote from Lawrence J. Peter. "Against logic, there is no armor like ignorance." I wish you well.